On item 2 of the first exam in fall 2014, we have a mass that is suspended attached to a ring by which there are two cables, one coming off at an angle of 25 degrees to the horizontal, and a cable that is horizontal off that ring and then passes around a pulley. We're asked to find what the force T is that's necessary to keep this mass in equilibrium. So the first thing that I notice when I look at this problem is that this cable that wraps around the pulley is just one cable alone. So whatever T I'm pulling down with here on the right hand side is ultimately going to just be a horizontal and the same force T attached here to the right of the ring. So I'm going to come in as my first step and cut away that ring as a free body diagram. And from that, we're going to eventually end up seeing that this is a very straightforward and simple problem. There's my ring. I've got the cable force T that I'm actually after going off to the right. That's horizontal. To the upper left, I have another force that I don't have a symbol for, so I'm just going to call it F, differentiate it from the other ones. And then I've got not a mass, but I've got, from a free body diagram perspective, I have a weight that is applied to the ring going downwards, and that weight is going to be equal to m times g. I'm right here, so I'm going to just go ahead and do that calculation. We've got 100 kilograms, so that's SI system, and associated with kilograms would be the acceleration of gravity, normally taken as 9.81, with the units of being meters per second squared for the KGS system. And that math is easy enough. That's 981 as a number. Kilogram meter per second squared is the same thing as a Newton. Right? And it's crucial that we do this work in terms of forces, newtons, kilonewtons, meganewtons, not in terms of masses. Masses are not forces. Okay. Once we have that, our next step then is to consider equilibrium. This is where the simplicity of this problem reveals itself. I look at this and I note right away that there are only two forces with x components. So the horizontal T, which we want, has to be balanced in some fashion by the x component of the other cable force. Right? So I could go at that directly and just work with x and y components, or I could look at this into a force triangle. Since I only have three forces, they do pass through a common point, which they would need to in order for this to be in equilibrium. In other words, a concurrent force system. And so I'd have the weight factor coming down at 981, the desired force vector of T of interest going horizontal, and then finally the other cable force F that turns out to be the hypotenuse of a right triangle. And that's what makes this problem really even simpler. It's already a little bit simple in the sense that we got only a three-force system to deal with. It's now even simpler because when we look at it this way, we recognize that, oh, that tangent of 25 is equal to opposite over adjacent. So therefore, what we were interested in, T, is just going to be 981 divided by tangent of 25 degrees, and that will be evaluated out at 2,103 newtons. The arbitrary rules that we have for this course are that if the number starts with a 1, we keep 4 digits in the significant digits, otherwise we only retain 3. And so that would mean that we would essentially want to get rid of the 3, round it either up or down appropriately. We will be rounding it down, which would leave us 2,100 newtons, or we can express the answer in kilonewtons as 2.10 kilonewtons. And there we go.